In this podcast, we're going to go over not only the physical properties of ethers, we're also going to go over some notable ethers that you may have in your everyday life. So your book likes to put together alcohols, alkyl halides, ethers, and thiols because they have similar properties. So we're going to look at a couple health notes from each of those. This first one is 2-mercaptomethylfuran, which is harder to say than it is to draw, and that's responsible for the aroma of coffee. Notice that it has both an ether and it has a sulfhydryl, so it has that thiol group as well as an ether. Sevoflurane is a common anesthetic that's used. It's an alkyl halide. Notice all the fluorines on there, the halogens, as well as it has an ether functional group in there. The trade name for this is easier to say. This is Taxol. Taxol is an anti-cancer drug, and notice that it has a decent amount of functional groups on there. We're focusing, of course, on all the alcohols or the hydroxyl groups that are present, but I also see amides as well as esters and ketones that are present in there as well. So a molecule like this would be very good practice for you to circle and identify all of the functional groups or the families that are present in this particular drug, because you'll be asked to do that frequently on exams and quizzes. All right, so ethers are kind of fun. They're really volatile at room temperature, and what that means is the liquid ether is going to escape readily into the gaseous phase at room temperature, or at very low temperatures. So oftentimes you will see ethers in the gaseous phase, which means they're very flammable. They have very low boiling points, which is why they can escape from a liquid to a gas at such low temperatures. It doesn't take much energy for them to overcome those forces that are holding the ethers to one another, so they can escape readily. They're relatively insoluble in water, but like with most of our families and our functional groups that we've seen, they're more soluble than hydrocarbons because they do have that oxygen. And that oxygen has a dipole-dipole bond, so it does have that slight negative charge on it, so it can interact with polar water, but it isn't as soluble as, say, an alcohol, which has that hydroxyl group and hydrogen bonding. As with everything, the longer the carbon chain gets, the less soluble the ether becomes. All right, so let's take a look at what I was describing on that last slide. So we're looking at dimethyl ether, and dimethyl ether is a very short chain ether, so it doesn't have a long chain of carbons, which would make it completely water insoluble. But when we look at an ether, we know that we have a shared pair of electrons here, and that there's a difference in electronegativity between your oxygen and your carbon. So your carbon is less electronegative, so it's going to take on a slight positive charge as those electrons are moving closer to oxygen. Oxygen, because it's pulling those electrons closer in that shared pair of electrons, is going to take on a slight negative charge. And we see the same thing for this bond over here. So we have these slight negative charges on oxygen. Because it has a permanent dipole, because it's showing dipole-dipole as an intermolecular force, this slight negative charge on oxygen is able to interact with the hydrogen on water. And remember, we have the same thing going on here. We have a difference in electronegativity between oxygen and hydrogen. Oxygen is more electronegative. Hydrogen is less electronegative. So between a water molecule and an ether molecule, we have a hydrogen bond that's forming. We have this intermolecular force. And so because we have that dipole in the ether, and water is able to surround this molecule because it doesn't have a long chain of carbons or a big nonpolar portion, and we would consider this ether to be soluble in water. Comparing physical properties like boiling point, butane is an alkane. It has all nonpolar bonds. It's a nonpolar molecule. Therefore, it has a relatively low boiling point. If we were to look at a 4-carbon ether, so we stick an oxygen, a 3-carbon ether, stick an oxygen in the middle of it, so this is ethyl methyl ether, we increase the boiling point. It's going to take more energy now to separate 2 ethyl methyl ethers from each other and have them escape from the liquid form to a gaseous form. When we add on that hydroxyl group, now we have hydrogen bonding between each of our 1-propanols. When we do that, notice, oh my gosh, our boiling point shoots up to 97 degrees Celsius compared to the 11 and the negative zero point 0.5 degrees Celsius. So adding that hydroxyl group is going to drastically increase your boiling points for similar carbon chain lengths for that molecule. So they can have very different boiling points based on which functional group is present. Diethyl ether is shown in the molecule above and is absolutely one of my favorite molecules to talk about. Diethyl ether was the first general anesthetic used in surgery. So this was used in approximately 1846. So back when surgery was not as sophisticated as it is now. Diethyl ether creates a loss of consciousness. So it causes a patient to black out. They also are going to lose their pain sensation. So whatever you're doing to them in the surgery, they're not going to feel. So you would typically take a mask or a rag that was soaked in diethyl ether and put it over the nose. This would cause the patient to lose consciousness. But remember what I said about having a high volatility or a low boiling point. So that liquid that's on that rag is escaping readily to the vapor form. Depending on how long your surgery is, you're going to start to fill that room, that surgery suite, with ether, diethyl ether gas, which, as I said before, is incredibly flammable. So a lot of times you'd blow up your surgery suite or it'd catch fire. You'd have these horrible accidents because of the way that diethyl ether was used. Patients would also wake up with really severe headaches and nausea as a result of using diethyl ether. So it was great at the time to use diethyl ether because before we started using diethyl ether, if a surgeon needed to perform something, they had two options. They would either use excess alcohol, so let's get you drunk to the point of passing out, you're not going to wake up or feel anything while you're passed out, or they would just hit you in the head with something and knock you out. Both of those are going to result in pretty severe headaches as well. So maybe those might even be better than an explosion. But diethyl ether, it is important to note, absolutely revolutionized the field of surgery. So very important molecule for us. Thankfully, we're living in a time of chemistry and we have alternatives to diethyl ether. These bottom images that you're seeing are safer alternatives, which cause unconsciousness, loss of pain sensation, but they have little to no patient discomfort, and guess what? They're not as flammable. So isoflurane, enflurane, and methoxyflurane are used in place of diethyl ether these days. All right, so here on this top image, we're seeing the molecule called dysparler. It is a ring ether, so we would call this an epoxide. You don't need to know that, that's just what it's called. This is a sex pheromone for the female gypsy moth, not that exciting. What is kind of concern is that molecule down below. This is hemabrevetoxin B, and this is a complex neurotoxin, and it has four ether oxygens, and this is produced by algal blooms that you would see in the ocean. So maybe you've heard of a red tide. A red tide happens, your ocean turns red when this algae proliferates that produces this neurotoxin. That is a time where it is not safe for you to be swimming because you'll come in contact with this neurotoxin and it will result in death.